Hello, everyone. Welcome to this lecture on reinforcement learning for conversational agents. Specifically, we'll be looking at reinforcement learning for task-oriented dialogue systems. My name is Haitham Farah. In what follows, we will be uh, first reviewing what a task-oriented dialogue system is, and we will be looking at the conventional pipeline for setting up task-oriented dialogue systems. And then we will see how we can leverage reinforcement learning to essentially make an end-to-end task-oriented dialogue system. So we'll see traditionally we have to split up the stages of a task-oriented dialogue system, the different modules. Um, Whereas with a reinforcement learning framework, we can collapse all those modules into one unit. So we'll be looking at this in what follows. So a spoken dialogue system consists of 5 parts. It's essentially a way that a user can interface with a system and receive a receive a response after inputting natural language input. So the user will speak as if he was having a normal conversation, and the system should respond in such a way that it seems like he's having a normal conversation with another human. A task-oriented spoken dialogue system is the same idea, with the one exception that the user is speaking to the system in order to accomplish some task, as the name suggests. Common examples are recommendations for restaurants, recommendations for movies. More interestingly, recently there's been attempts to make spoken dialogue systems that can tutor students and that can help them progress in whatever subject they're studying. So interesting stuff. So the pipeline for a spoken dialogue system is presented here, and it starts with the user, and the user inputs into the system natural language utterance. So this is just spoken sentence, a common everyday spoken sentence. The first module of a spoken dialogue system is the natural language understanding unit. So first, the system has to interpret what the user is saying, but not merely. This is not merely an NLP task. It's not just, for example, processing raw sound data and turning it into text. It has to understand what the user is trying to accomplish with his utterance. Once that's been done in the natural language understanding unit, um, the state tracker will modify the state of the dialogue. So if the natural language understanding unit finds that the user is looking for a restaurant, then the state tracker will note that the system should now be trying to find a restaurant. If the user then specifies that the restaurant should be an Italian restaurant, the state tracker will then put that as a condition for the restaurant that it is searching. So it tries to find what it ought to be doing, what it ought to be giving back to the user based on the history of utterances that the user has input into the system. And once it has a solid map of the state of the conversation, it forms a dialogue policy. And this basically, the policy will determine what the system will output to the user in order to receive the next verbal utterance from the user. So, for example, if the system needs more information, the verbal action could be a clarification. If the system wants to suggest something to the user, the next verbal action could be a recommendation. So at this point, a verbal action is not yet in the form of natural language, but more in the form of what the system is hoping to accomplish. Um, it's only in the next unit, the natural language generation unit, the NLG unit, where the system then uh, from the verbal action chosen by the dialogue policy will generate an utterance that sounds like, natural language that humans would engage in. And once the system has spoken back to the user, the cycle continues over and over again until at some point, hopefully, the user is satisfied because the task that he was hoping to accomplish has been achieved. Just to make the idea of a dialogue act a little more concrete, I've taken this table from an essay about spoken dialogue systems for tutoring. We can see plenty of examples here of dialogue acts, and we can see that they can either come from the user, and or they can come from the system. So if they're coming from the user, like, for example, request for feedback here, as you can see, it's coming from the student. That means that the natural language understanding unit will interpret one of the utterances as a request for feedback. And this will, of course, inform the dialogue policy and the state tracker. In other cases, we find that, like in the first example, it's the tutor that's actually, um, you know, performing the dialogue. And in this case, it is the output of a dialogue policy to say that the next thing I want to do is give a hint to the student. And then after receiving that dialogue act, the natural language generation unit will make a hint in the form of an explicit natural language sentence. So this table, I think, will give you a decent idea of what a dialogue act may look like. So now we can talk about two of the major challenges that face spoken dialogue systems. So the first challenge is the credit assignment problem. And what this means is that when there's a problem that happens, it's often very difficult to locate which module is the source of the error. So it could be the natural language understanding unit, or it could be the state tracker or the dialogue policy. And generally, it's not straightforward to figure out where the error is occurring. This could be very expensive and time consuming and intractable in many cases. The second challenge that faces spoken dialogue systems is process independence. So, assuming I want to optimize the state tracker, well, then the dialogue policy may become suboptimal because it was originally trained on a different version of the state tracker. So, it's hard to update one module out of the whole pipeline without um, rendering the performance of the other parts suboptimal. So there's no way that we can independently work on one of the units, and this will be another major challenge that faces spoken dialogue systems. So the authors propose, as a solution to both these problems, to combine the modules into one module and to use reinforcement learning in order to achieve this. So they're not going to be too concerned with the natural language generation. What they're interested in is combining the natural language understanding, the state tracker, and the dialogue policy. Everything in this box here, and we could see once if we imagine that this is all one unit, that it starts to look like um, reinforcement learning problem already, where the user inputs some utterance, and that's their observation from the environment, and they have to respond in such a way that satisfies the user's in, intention, or satisfies the task that the user wants to accomplish from the system. And upon satisfaction of the task, the agent will receive rewards. So we can see it's suitable to a reinforcement learning framework. So this figure outlines their new pipeline, and we will be, for the remainder of the presentation, we'll be looking into more detail as to how their pipeline will work. So we could see the RL problem being formed in terms of two environments, a user environment and a database. Um, and uh, uh, they can receive separate observations from the user or from the database, separate rewards from the user or from the database, and they can do an action that either interfaces with the user or with the database separately. So we'll be going into more detail as to what verbal action, towards the user may look like, or a hypothesis action, as you can see here, what that means, and we'll also be explaining later what the hypothesis itself is. We could see that this will take care of many of the challenges facing the conventional spoken dialogue systems that we've been over, because now it's simply one end-to-end system that can be optimized all at once. So the one part of this that's non-standard for RL is that there are two separate environments. That's how the authors choose to model the situation. So it's just important to note that there is a user environment and there's a database environment. And in terms of the user environment, it's a little more straightforward. So a dialogue action would be an utterance directed towards the user. So remember, in the new pipeline, they're not too concerned with the natural language generation. So we're just worried about outputting the right dialogue action, and then we'll assume that the natural language generation part is taken care of. Observation, of course, is the user utterance, what the user inputs into the system in terms of natural language. The true state would be what the user intends, and the rewards would be, for example, user satisfaction or the completion of the intended task, what they call the user rewards. What's less clear is what the database environment will consist of. So the idea behind the database environment is that in order to accomplish the task, the system will need to retrieve information from a database. So usually the task that's requested of the system is of the form of finding a specific piece of information from a database. And the spoken dialogue system simply, it gives the user a very friendly UI in order to retrieve the required information from the database. So what we'll be largely going over from now on is what the database environment is, but essentially the idea of it's a way for the system to interact with the database to approximate what it is that the user is looking for more and more closely until the user is satisfied with what the system is retrieving from the database. So the intuition for now, a hypothesis action, will simply um, modify what the database should be searching for. It'll tell the database, find something that satisfies um, these requirements. So a hypothesis action will simply be a modification of the hypothesis. So it'll change the conditions that whatever needs to be retrieved must satisfy. So the observation from the database will be anything that satisfies the hypothesis, but the true state would be the one object that actually needs to be retrieved from the database. And database rewards, we will see, they'll actually use database rewards in order to create more efficient algorithms. So we will be going over what a hypothesis action is in more detail, as well what database rewards are. So the hypothesis, as we briefly touched upon, determines what information is retrieved from the database. Um, so we could see that a hypothesis will be composed of n slots up here, and these n slots could take on different values. So for example, slot number 1 or number 0 could be what sort of entity is the user searching for, and the value could be a restaurant, or it could be a movie. So if it's a recommender, um, the second slot could be perhaps the genre of the movie or the kind of restaurant, and the values that it takes will reflect more specifically what the user is looking for. So what the authors are using this for is as stand-in for tracking the state of the dialogue. So now they don't have to have a separate state tracking unit. They simply have a hypothesis that the system can directly act upon, the RL agent can act upon in order to retrieve what needs to be retrieved from the database. And as we mentioned before, the hypothesis action modifies one of the values in the slots. So a hypothesis action might change the genre slot that we were talking about from unknown if the user doesn't specify what he wants to horror. And that might help the system retrieve the right element from the database. Now, the way we want to engineer a database is in such a way to help our algorithm converge faster to the correct element. The way we'll do this is by introducing a pseudo reward function f and adding it to the end of the standard reward function. F is defined in terms of the potential function phi here. Now, what is the potential function? Well, it consists of a couple of variables. Firstly, the total number of elements in the database given by big D. Then small dt is the number of elements being considered at state st. And Pmax is a constant that we choose beforehand. The authors choose too. And the reason it's called Pmax is because it's the maximum value of the potential function. And the intuition behind here is that the fewer elements that we consider, the higher the function will be. So if we only consider a small amount of elements here, dt, then the thing we're subtracting 1 by will be itself quite small. And so it'll be as close to the maximum value as possible. Now, of course, we don't want our agent to consider no elements of the database because that will not help the user with his task. So if at any point dt will be equal to 0, we're going to set the uh, the potential function itself to be 0. And the whole idea behind this is to reward the agent for narrowing down the database as quickly as possible. And we'll just add this on the end of the standard reward function. So the reinforcement learning agent will be trained with a combination of an LSTM, long short-term memory network, and a DQ network. Now, it is very common to use a long short-term memory network in order to represent the belief function of an underlying partially observable Markov decision process. And that is exactly how the LSTM is being used here. At each time step, the long short-term memory network will take in several inputs, namely the previous action, the user observation, in other words, the user utterance, and the database observation. And it'll be taking in the previous belief from the previous time step. Now, the output will be fed into a deep Q network, which has one hidden layer and a 10H activation function. And with the Q value, the network will proceed with an epsilon greedy policy. As you may notice that some of the deep Q networks are slightly lighter. And the reason for this is that at each time step, the reinforcement agent will only pick one of the two possible actions. Namely, it'll either pick a verbal action to execute, or it'll pick a hypothesis action, changing the hypothesis of the database. And the reason for this is purely for efficiency, so that at each time step, the agent doesn't have to pick between every possible action, but only a restricted subset, and it'll alternate at each step between the two. This is what the authors call the action mask, but it's a very simple concept, and it's just about alternating between different actions at each time step. In order to see how well their new framework works, they will be testing it out on the 20 questions game. So the game works as follows. First, the user thinks of a famous person. They have a list of 100 famous people pre-selected. Then the agent is allowed to ask the user 20 yes or no questions about the famous person. User has to answer honestly with any natural language utterance. Yes, no, or I don't know, something of that form. The any natural language utterance is important because of the fact that the authors are trying to essentially replace the natural language understanding. So to test out how it works, they need to allow the users a broad range of responses. So of course, if the user says certainly, that counts as yes, or I think so, that's a yes, or yup, that's a yes. The game terminates when the agent guesses the correct answer, in which case the agent will receive 30 plus rewards. It also ends, in this case it's a loss, if the max game length is reached, 100 steps, or nobody in the database matches the current hypothesis. This will result in minus 30 rewards. So do note that the discount factor is 0.99, so this will incentivize the agent to achieve the correct answer as early as possible in the game. And wrong guesses which can occur up to 10 times, will result in a penalty of -5. So of course, more than 6 wrong guesses, it's as if the agent has lost. So more specifically, the implementation of the 20 question game has the following constraints. So first, a pre-selected number of famous people are chosen, 100 famous people. Each famous person has 6 attributes, namely their birthplace, their birthday, their degree, their gender, their profession, and their nationality. And the agent has 31 different questions to choose from at each step. The figure on the top right gives you a summary of the available questions. For each attribute, the corresponding number of questions is given by this column here, QA, and an example question is provided. In order to train the agent quickly, simulator is used to simulate what a human may input into the spoken dialogue system. So the simulator works as follows. First, it samples one of the famous people randomly. And then for each of the 6 attributes, there's a 5% chance that the simulator will mark that attribute as unknown as opposed to the correct value. And then when the agent is interacting with the simulation will respond with a series of natural language responses generated from the SWDA corpus. So the SWDA corpus provides a series of natural language utterances with the intent behind them. So as you can see from the table here, they collected utterances with the intent of yes behind them, with the intent of no, and with the intent of unknown. And the frequency with which these utterances appeared is sampled according to the same distribution that is found in the SWDA tags. So if a word appears more frequently in the SWDA database, then it's more likely that the simulator will respond to the the spoken dialogue system using that natural language utterance. To conclude, we will look at the results of the experiment and compare it with the traditional way of implementing a spoken dialogue system. So baseline here refers to a standard spoken dialogue system that has the separate modules, as we discussed in the beginning, a separate dialogue policy module, a separate state tracking module, and a separate NLU module. The RL algorithm, the RL row corresponds to the agent that we have been describing throughout the slides. The hybrid RL one is almost the same thing, with the one exception that on top of the pure RL approach that we've been discussing, uh, there is also a supervised learning done in order to help the agent classify the labels better. So we can call it a boost to the NLU part of the agent, just to help it classify statements better and thereby modify the hypothesis more accurately. So as we can see, the baseline actually rushes to guess far more quickly than the RL or the hybrid RL approach. We can infer that this has something to do with the fact that the baseline doesn't learn with the idea of maximizing the rewards. It more or less uses standard supervised learning approaches, whereas the RL is attempting to win the game. And we can see that the hybrid RL actually performs the best in terms of having both the highest win rate while maintaining a slightly fewer average turns than the standard pure RL approach that we were discussing. In order to better understand the win rate results, we may look at how the different algorithms did with respect to tracking the state of the conversation, which essentially was represented by the hypothesis in the RL case. So here we're comparing how each of the algorithms did in terms of their classification precision and their recall. Just as a quick reminder, precision is the ratio of the correct guesses to the total guesses that it made. So the higher the precision, the less that there are false positives. Whereas the recall is the correct guesses made divided by the total number of possible correct guesses. So a higher recall rate means that it is more likely to find correct label. It's not going to leave a potential label out when it's there. So we can notice the probably most glaring is that the baseline precision for unknown is much higher than the RL algorithms. While this may seem to suggest that the baseline is therefore more accurate, another way to interpret this is that the RL algorithm actually predicts unknown when the input is ambiguous because it's a safer option than predicting yes or no. Confusing between yes and no may potentially lead to a contradiction and a complete failure in the game, whereas unknown doesn't quite render the whole game lost if you misclassify an unknown. So the RL algorithms, we can see there the way the way they classify and the rate at which they are precise with the yes, no, and unknown labels actually reflects a certain strategy that they are pursuing in order to optimize the game. This is actually a very interesting and promising result for the reinforcement learning framework, since it suggests that insofar as there's a task, the RL algorithms are best able to optimize for that given task, and could be something worth looking into more in future research. Overall, there are a lot of exciting developments in this paper, not only for the vast literature on reinforcement learning, but more specifically, the novel approach for tackling the dialogue state tracking problem suggested in this paper. Whereas conventional dialogue state tracking worked via supervised learning, the new approach leverages reinforcement learning so that the way that the dialogue state is being tracked actually optimizes the completion of a task. Furthermore, this work provides important contributions to the field of end-to-end spoken dialogue systems. Briefly, an end-to-end spoken dialogue system is a model that can back propagate error signals from the end output to the raw inputs. by eliminating all the individual modules, like the natural language understanding module, the dialogue state tracking module, and the dialogue policy module, combining it into one reinforcement learning agent, we effectively overcome the two main challenges we discussed at the beginning, namely the credit assignment problem, where it's difficult to find the source of the error, and the process independence problem, where it's difficult to jointly optimize all of the systems at once, or rather difficult to optimize one on its own without negatively affecting all the other systems. So some of the future challenges that this work could use in order to improve it and take it to the next level is improve the sample efficiency. If we look back at that graph uh, at the win rate, we see that the baseline, although converges to a lower overall win rate, converges to that win rate much quicker. So finding ways that we can increase the rate of convergence would be useful for constructing such models. Furthermore, more thorough empirical evaluation is in order. The 20 question game is a good way to get a feel for how this new spoken dialogue system would work, but more thorough testing could give us better understanding of the strengths and weaknesses of this approach. And finally, we saw that since the hybrid RL approach actually worked better than the normal RL approach, it's worth looking into techniques that allow us to integrate domain knowledge so that we don't have to simply rely on a pure RL technique. Rather, we can leverage RL where it's useful, but also integrate domain knowledge in order to achieve the best level of performance. All these are potential avenues for future research.